good? Good. All right. So, one thing I just wanted to follow up on, the basic idea of an angle. Started talking about it and I didn't get all the way through it. So basic idea of an angle, one way to think about an angle is a rotation or part of a rotation. And so let's just consider a shape that we can rotate, rectangle. So here's my rectangle. I can make a copy of that rectangle thing. Use my bag pen. Copy. Paste. So here's my copy. And this program is lovely enough to give me a tool for which I can rotate it. And it's got this little snap to grid feature, so I was able to rotate that just through part of a turn there. And so if I start, and when we do rotations, there's always going to be a central point to think about. So I have some central point. I have some starting direction. And then I start to spin somehow. I start a turn of a rotation. And so if I start in that direction and then keep rotating and end up back where I started, like that would be a full rotation. And I could do something like just turn and look the other direction. So this red rotation here would be a half of the rotation. What I did from this shape to this shape right here, if I did a quarter of a rotation, they would look the same. So from here to here, I did 1/8 of a rotation. Does that seem reasonable?
Yeah.
So I can grab it and kind of demo that. So I can click on this object. So a full rotation would take this green point and put it back on the top. A quarter of a rotation, or a half rotation would put that green point on the bottom. A quarter of a rotation would put it on the side, making the shape look exactly the same way. So it looks like I had to do 1/8 of a rotation to get it to it that way. And we can talk to kids about fractions of a turn. We have a full turn, a half turn, a quarter turn, and so on. So that's one way to talk about angle. That's not how we usually talk about angle, though, is it? A usual way of talking about angle is in degrees. Why? Why degrees?
There's 360 degrees in a circle.
Why? Why 360? I wish there were 100 degrees in the circle. 100 is way easier to manage than 360. So let's talk about that next. So again, one way we can measure an angle is by a rotation, a fraction of a rotation, or a turn. But we have this idea of degrees that we use often. Let's consider that. And again, for any rotation, you have some central point, you have some direction that you start at. Maybe I'll start at that direction facing up. And from that direction, I could choose to turn. And so maybe I turn and end up exactly where I started. So I could call this one turn. I could call this one revolution. Call it one rotation. I could also call it 360 degrees. And we got that silly little circle we put for degrees there, which we've gotten very used to. Some kid might ask, well, why do you put that silly little symbol there for degrees? So I always have. We'll check on that symbol later. But why 360? It's very close to another popular number in our world. Well, the compass is the same idea, but why? The compass uses 360 degrees, but why? Days in a year is where it comes from. Oh, there's 365 days in a year. 360 is easier to manage than 365. And so we've been using 360 for a long time because it takes about that long to get around the sun. It's a convenient number to work with. There's a lot of divisors, which is nice. I just consider the divisors of 360 for a minute. See if we can do a little review of divisors just for fun. All right, we got 1 times 360 would be 1 pair. So we get complementary pairs. We're like 2 times 180. 3 times 120. 4 90s. 5 72s, I think. Double check that one, but it sounds right. Yeah, it sounds right. Yeah, that's right. 6 60s. No 7s, but there are 845s. The list keeps going. Let's see, do we have any 9? Yeah, we got 9 in there. We've got what, 9 40s, 10 36s, 12 30s. I'm kind of looking at the other numbers to help me figure that out. 3 times 120 versus 12 times 30. Let's see, 12, 13, 14's out 15. Yeah, 15 times 24, I think. I don't know how to calculate it there by the end. Pretty sure it's 15 times 24. 3 goes into 72, 24 times, yeah. So 15 times 24, let's see, well, 16. 16 won't work because 8 times an odd number. 17, 18. Oh, 18 works. 19 times 20. And then I'm done. Because 19 is next, and then I start repeating myself. Man, 36 is a lot of factors, which means you can break a full rotation up into a lot of different whole number, equal whole number parts. So there's nothing special about 360 besides it's close to the number of days in a year, and it has a lot of factors. And somebody decided, hey, this would be a nice way to split up a rotation. Could I split up rotations other ways? Sure. We could split up rotations in percent rotation. we could have 100% of a turn. That would be going in a complete circle. 50% of a turn. Half a rotation. 25% of a turn, and so on. There's all kinds of different things. There's another unit of measurement that's really popular in math that we'll get to hopefully by the end of class today. I think I want to hold off on that for now. So we use 360 for a couple of special reasons. One, it's close to the number of days in a year. Two, it has a lot of nice factors. Otherwise, it's not all that special. It's kind of arbitrary. It's way more arbitrary than having a base 10 number system. We get a really good reason for that, right? 10 fingers. Excellent reason for a base 10 number system. We could have had a base 5 number system. That could have worked out just as well for us, because we had 5 fingers on each hand. But the degree is 360, pretty darn arbitrary. Way more so, I believe, than base 10 number system. Okay, so we have different ways to work on degrees. We are very used to 360. Kids are going to have to get used to it, but they can totally get used to doing a full turn, or a half a turn, a quarter of a turn. So we can play with those ideas, and then eventually they'll get used to 360, 180, 90. Like, I really got interested in angles when I started skateboarding as a kid, because people used to talk about doing a 360 or doing 180. It's like, oh, angles, cool, math, I'm skateboarding with math. All right. So there's one more angle measure we'll come back to when I back up again, section 7.2. Polygons. So I think I better open up GeoGebra for that. Let's see what other polygons I can get out of this tool. I can get a hexagon. Let's do a pentagon. It doesn't even have to be a regular one. Let's do a regular pentagon. Like that one. Let's see. So just a couple of reminders where this line right, tool, Control Z, marker, this line segment right here is also referred to as an edge. We call it a side, but once we get into 3D geometry more, we really need to be careful about the use of the word side, because we use it to mean multiple different things. If I have two edges that are adjacent, they meet at a vertex, and adjacent edges form an interior angle. And in project number 7, activity 7, we developed a formula for the sum of the interior angles of a polygon. I'll play around with that idea a little bit more with verbal algebra just for fun. So that's an interior angle. Exterior angle is kind of a confusing idea in geometry, so we're going to be a little bit careful with that. If I were walking along this bottom line segment right here, I could keep going, but if I wanted to stay on the line, on the polygon, I would have to make this outer rotation right here. And that outer rotation is what we refer to as an exterior angle. line I would have to turn through if I were walking around the polygon. Angle. I must turn through. Stay. Walking. So we have edges, edges can be adjacent. Adjacent edges have an interior angle. Adjacent edges also have an exterior angle, which is a very specially defined angle. And then we came up with a way to measure an exterior angle, the sum of exterior angles. So let's review that. Sum of exterior angles. Let's see if I can properly draw this picture. Here. Polygon. Close enough. So consider this situation here where I have a polygon whose vertices, let's say they sit on the circle. And consider two things here. One, walk around a circle. Through what angle do you turn? That's one question we'll consider. Other question we'll consider, almost the same, walk around the polygon through what angle do you turn? And my claim is they're, as far as angle, not distance, they're the same question. So let's get another shape. So, let's suppose I start here on this top point. And I walk around. So I walk around the circle. And the question is, if I walk around the circle, through what angle did I turn? So that would be kind of like me grabbing this green dot here. If I grab that green dot and I move it around, when does it go back to pointing the way it started? Well, not until I get all the way back to the top, right? So I've turned, I've spun as I walk around this thing 360 degrees. Same thing happens to be true on a polygon, because if you think about it, it's a highlighter, walking around the circle is a lot like walking around the polygon. You're just kind of shortcutting as you go, but your body is turning the same way as it would on a circle. Does that make sense? Okay. And the significance of that, those colors, the significance of that idea is with respect to exterior angles. If I extend each side a little bit, as follows. The exterior angles represent the turn I had to make to stay on the red polygon. And if I spun 360 degrees, that means one of these exterior angles had to be 360 divided by the number of sides. And so I can pretty much translate that to any convex polygon. Doesn't matter whether it's 5 sides or 3 sides or 4 sides or 20 sides. Any individual exterior angle is always going to be 360 divided by the number of sides. I'm pretty sure that's 72 here. For the 360 chart. Yeah, 5 times 72 is 360. So a single exterior angle on a pentagon is 72 degrees. Now, some other things that are kind of cool about that idea. Let's get a new screen. Let's get over messy. New screen. Let's get ourselves another pentagon. Pentagon. Solid line. Black. Work. Here's a pentagon. And then consider one. Oops. Many tools. Consider one of these exterior angles here. So that's the exterior angle, right? However, on the inside, I have an interior angle. And can you tell by looking at the picture what an interior angle added to an exterior angle has to be? Yeah, it's always going to be equal to 180. So another thing I have at my disposal, if I know the interior angle and the exterior angle add up to 180, then I can always use one to find the other. So if I know the exterior angle, for example, then the interior angle is always going to be 180 minus the exterior angle. Just join us. Hi, Kelly. So we had developed a formula in class with that activity 7, I believe it was, to come up with the sum of the interior angles of a polygon based on how many sides it had. So I'm just going to develop that in a slightly different way here. So we now have a rule back here for how to come up with the exterior angle of a polygon. We take 360, divide by how many sides. Now it's going to be a convex polygon that's important. We'll take a look at a concave polygon in a minute. So I have a convex polygon, take 360, divide by the number of sides. That's the exterior angle. Write that down here. So 360 over n is the measure of an exterior angle of an n-gon. We also know that the interior angle is always 180 minus the exterior angle. So let's throw that in. So the interior angle is equal to 180 minus the exterior. Well, the exterior is always 360 over n. So that gives us a single interior angle. Okay. Next, we were looking earlier for the sum of interior angles. And I should repeat something. I don't know if I said clearly earlier. When I'm doing this part right here, it's a regular n-gon. I think I did not include that fact. Because if it's not regular, that means the angles are all over the place. You never know what you get. But we can use this to point at the interior sum of angles. Well, let's see. If this is one of the angles, and I have an n-gon, can I just multiply that single angle by n, scale it up? That gives me all the angles, all n of them. And we'll test this out on a regular pentagon in a minute. So I think for a regular n-gon, some of the interior angles is going to be equal to n of those single interior angles, which are found by taking 180 minus 360 over n. We'll try cleaning that up and see what it leads to. So pieces we put together again. If it's a regular n-gon, 360 over n is an exterior angle. Interior angle, the interior and exterior have to add up to 180. So 180 minus 1 gives the other. So we have a single interior angle. If it's an n-gon, it's going to have n of those interior angles. All right, so now we're going to mess with this formula and see what happens. So let's see. I'm dying to distribute that n through there. A little algebra, we haven't done much algebra. So that's going to give me 180n minus, and then let's see. What happens if I take n times 360 over n? And I distribute that through.
The n will go away.
Yeah, the ends are going to cancel in that second part. So then in that second part, I'm just going to get minus the 360. Now, thinking back to algebra class, what kinds of things did we do in algebra? Well, distributing is pretty popular. Factoring was also pretty popular in algebra. Is there a common factor to these two terms? What number goes into both? What's the biggest number that goes into 180 and 360? Yeah, 180 goes into both, so we can pull out the whole 180. So we pull out the 180, and then we have an n minus 2 left over. And if you think back to our work on activity 7, we had a formula that said if you have an n-gon, there's always n minus 2 non-overlapping triangles inside of it. Double check. Pentagon. If I start drawing diagonals, I'll find that any pentagon can be split into 3 triangles. 5 minus 2 gives me those 3 triangles I see here. What's the interior angle sum of any one triangle?
Total 180.
That's 180, yeah. And so there's a 180, here's another 180, here's another 180. Altogether, I've now used those 3 non-overlapping triangles to build all of the interior angles of my pentagon. So there's my 180 times 3, which gives me the angle sum for a pentagon. I went about it kind of a weird way. And to do so, I had to restrict myself temporarily to regular polygons. But it turns out the result is a little more general. But this right here is the formula we developed a completely different way in class last week for the sum of interior angles. So just a reminder what that formula means. Sum of the interior angles actually, it was regular when I was talking about the exterior angle. At this point, it's any polygon. The 180 times n minus 2 applies to any polygon. The part where I got stuck with just regular ones was when I defined the exterior angle as 360 over n. That's only if every angle is the same, which means it's regular. Well, angles and sides are the same would be regular. Can you have a polygon that has all the same angles but isn't regular? Can you think of an example that fits that? All the angles are the same, but the sides aren't, so it wouldn't be regular.
Every time you pose that question, usually the answer is yes, so I'm going to go with.
You're going to go with yes.
Not that I can think of it off the top of my head.
Yeah, so if we kind of play around and draw a little bit, like with a triangle, it's kind of hard because if I make all the angles the same, like here's a 60-degree angle and then there's a 60-degree angle, I'm stuck with another 60-degree angle and the sides get stuck being the same. If I mess with a 4-sided figure, 4 goes into 360, 90, right? So each angle would have to be 90. So there's one side, there's a 90-degree angle, here's another 90-degree angle, here's another 90-degree angle, and it says, oh, well, look, a rectangle would be equiangular, but not equilateral. And so it turns out you can have an equiangular figure that's not equilateral. Think about a pentagon for a minute. Can we make a pentagon? Let's see, I think that would shift and give me a regular pentagon. Yeah, so there's a regular pentagon. And let's see. I can't do it with this drawing tool, I don't think. Let's try, maybe I can. I'm not sure if that actually happened what I was thinking. No, it didn't quite work what I wanted. Imagine just extending this side and this side by the same amount so that these two sides got longer than all these other sides. I could maintain the angles being the same while making the figure bigger. Is that true? Or am I lying? My brain just said, "You lying, Gary."
Well, it's definitely look better than the rest.
All right, let's try it in GeoGebra.
But
So GeoGebra is a great playground.
The angles are still the same? I don't know.
So let's see, as I was stretching that, so
So you can kind of visualize it here. I was trying to just stretch it vertically. Oops. And since I'm pretty sure that angle is changing at the same time, let's get GeoGebra and ask. So whenever I get a problem in my head that I can't feel like I can find an analytical way to solve it, I whip out an experimental tool or my compass and my protractor and my straight edge. So let's go to GeoGebra. Remember in GeoGebra, we always have that quick start GeoGebra. It behaves a little bit different than the desktop version. Okay, so let's see. I want to try to build a regular pentagon. So if it's a regular pentagon, it would have to have 70. What do they measure the interior angles? Let's go back. It would be interior angle would be 180 minus 360 over 5, which is 108. So each interior angle should be 108 degrees. So what I could do in GeoGebra to try and build that is start with a line segment. Let's get my grid, and let's make this viewable to the studio audience. Font size 20. And let's go down here and say my first line segment is going to be 2 units long. And then I want to measure an angle of a given size from B through A. And I want it to be 108 degrees because I'm aiming toward equiangular. So I'm going to try and build equiangular but make the sides different. See if I can do it. So I click OK. And so here is that angle starting my pentagon. And so I'm just going to kind of try to keep going around building that. So then I'll build a ray through that. We did this in class the other day, playing around. Okay, so GeoGebra draws B prime here so that it's the same distance from A as B was. Okay, so it's using a compass basically to draw that. So I think I want my next one to be farther out than that. So I'm just going to pick some point out here further, like maybe right here. And then I'm going to head out 108 degrees from there and see what happens. Okay, so angle of a given size from here through there, and there's 108. So here's my next one. And let's see, I need to draw a ray. Here to here. What do you think? Can I do it? And let's suppose I want to have that same length 2 that I had down there. The only way I know to do that with GeoGebra is to use a circle with a given radius. So I go here, so let the radius be 2. So then this point right here where they intersect would be like the line segment AB down here. Same length. And some people play video games. This is my video game. All right, let's turn off that circle. Oops, not the ray, the circle. There we go. Okay, so then I'm going to come out from that point, 108 degrees. Oops, how'd that happen? Just came back on. Fascinating. 108 degrees. Okay, so here's my point C prime. Yeah, see, can you see the symmetry? C prime really doesn't line up symmetrically. So this is, I might not be able to do what I wanted to do. That doesn't mean there's not another way to do it. Okay, so I have 108, 108, 108. I want to try and get back here with 108. So what I could do is head out 108 from B and see if what angle I hit there with. So let's try it. So let's see, I want angle measuring tool from A to B, other way. Okay, so this would be clockwise. Hey, Debbie.
Hello.
We are experimenting. We are
Okay.
trying to build an equiangular pentagon that isn't equilateral.
Okay.
This question kind of popped up in class. And my first guess was that we could easily build it, and so now I'm trying in GeoGebra. So if it's equiangular, we figure every interior angle has to be 108, based on our work in the last project. Okay, so so I did it if this last angle is 108. Does it have to be 108?
To be angular.
Okay, to be a pentagon. Well, how many 108s do I have already? I've got 4, right? Is the angle sum of a pentagon a fixed number? It is, so it looks like this last angle has to be 108. And so it looks like it can be done. So let's just double check with GeoGebra. If I go from this line to this line, is the angle in between 108? Now I did the wrong one, but there's a theorem we'll get to in a few minutes that says if two angles are vertical to each other through intersecting lines, they're equal. Anyway, I'll just redo it. I should have clicked it this way and then that way. Okay, Control Z. Let's do it this way. Find the intersection points. And let's say I have to do it clockwise. So angle tool, I have to click on C prime, E, A prime, and there's my 108. All right, so that got a little messy. Let me clean it up so you can see what the heck I actually did there. Turn off the circle. Let's turn off some of these rays, that line segment, and I'm going to trace out my polygon. Let's say point B, point A, point C, point D, point E, back to point B. So here I have an equiangular pentagon that is not equilateral. Before that, we answered the question, can we have a quadrilateral that's equiangular but not equilateral? All right, so yeah, it turns out that the only place, if we have equiangular, we're stuck with equilateral. By observation so far, seems that's true for a triangle. It's not true for a quadrilateral. It's not true for a pentagon. Is that enough evidence to say we can do this for any polygon? Not quite enough evidence, but it's heading that direction. All right, so let's go back. Let's see. Where were we here? Sum of interior angles. Okay, I think I almost beat that to death. Exterior angles. One thing we didn't talk about too much yet, but is in the book in section 3, are symmetries. So let's go over that a little bit. So we're kind of catching up on topics in sections 1, 3, and 4 that we didn't get to through the activities we've been missing. This is in 11.3. And then it comes up again in chapter 12 or 13, maybe both. Let's see. It comes up again, yeah, in chapters 12 and 13, it comes up again. It's a pretty common topic in math. So there's a couple of different kinds of symmetry. There's line symmetry. And there's rotational symmetry. Hang on one sec. Okay. So examples of each. Let's pick on pentagon for a minute. In a lot of programs, you can make regular type figures with drawing tools by holding shift down. So if I don't hold shift, I could get a tall, skinny pentagon. If I hit shift and then try and move, it'll make everything regular in it. And then let's switch to the line drawing tool. If I draw a vertical line through that peak there, this has a line of symmetry passing through that splits in half. How many lines of symmetry does a regular pentagon have? Well, I've got that one line there. And then if you think about this point over here, I have a line through that point. And then, let's see, do I have the line through this point yet? No. Let's try that one. There's another line of symmetry there. Do we have any others? I'm running out of color. And kind of missed on that one. How many lines of symmetry does it look like a pentagon might have? Let's try orange. What's that? 4. Oops. 5 lines of symmetry, yeah. Let's try. It's pretty close. So this has 5 lines of symmetry. So we can. This is an idea we can play around later. How many lines of symmetry can a particular figure have? And so any line that splits it symmetrically, so each side is a mirror of the other, is a line of symmetry. Oops, I accidentally turned one of my lines. There we go. So if I move any of these out of the way and just focus on one of them, because it gets kind of messy, we should be able to justify to ourselves that this orange line splits this figure in half, so that one side is a mirror image of the other side. And often lines of symmetry are going to go hand in hand with rotational symmetry. So for this figure right here, if I rotate it a certain amount, it should look the same as it did before. So how many incremental rotations would I have to make till I get my original top vertex back to the way it was? And it looks like I made 5 incremental moves to get it back to the way it was. So this has a 5-fold rotational symmetry. That's 5 lines of symmetry. Now that's just want to turn the volume off. Apologies. I actually hit snooze. Okay. And so we can spend a long time studying different kinds of symmetry, but the basic kinds are line symmetry and rotational symmetry. And for regular figures, they go pretty much hand in hand. If the figures aren't regular, it's not necessarily going to go hand in hand in terms of the symmetry. For example, let's take a different pentagon. Ooh, let's do a 5-pointed star. Those are fun. So let's take this 5-pointed star right here. How many lines of symmetry might this thing have? Well, for sure, I can make this one right here. So there's one line of symmetry. The question is, if I move this line a different way, or if I rotate this figure, will it look the same? So if I try to draw a different line, like let's move this guy out of the way for a minute, and draw another one, let's pick a new color, like maybe through this one here, does that cut this figure in half? Like the black line, cut this in half symmetrically. Doesn't do it. So if I folded on that blue line, would all of the orange lines line up? The answer is no, they wouldn't. Okay. So here, this could have been a regular pentagon, a regular star, but I chose to make it irregular by stretching it vertically. Think about
Regular it would work.
yeah, so regular figures have lots of symmetry. They're easy and fun to work with, right? But once a figure gets irregular, then it becomes a little harder to work with in terms of symmetry. So like here, I'm going to rotate this. And the question is, through what angle do I have to rotate it till I get the same shape again? And so here, if I rotate it just a little bit, is that the same star I started with? Nope. Is that the same one? Nope. Here? Nope. 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 Yeah, so I have to do a complete rotation before I get back to where I started, which basically means I don't have any rotational symmetry. Because every figure that's true for. Right? Draw the craziest shape you want. Rotate it 360 degrees. You have the same crazy shape and the same orientation.
Lines of symmetry.
That is a good question, and that was going to take some time to address. How do the lines of symmetry relate to the rotational symmetry? And it depends on the figure. So here I have one line of symmetry, and I have no rotational symmetry. With the previous figure I had,
Okay, wait. You have none.
I have one line of symmetry here, but I have no rotational
So the
symmetry.
rotation doesn't count if you have to go all the way around.
If you have to go all the way around, it's useless, right? Because you can take the craziest looking blob
Okay.
or tree. If you rotate it 360 degrees, it's the same blob or tree. Okay. So 360 degree rotation is not helpful. It's got to be something else. So this has one line of symmetry, but it has no rotational symmetry. Whereas my regular pentagon here had 5 lines of symmetry and a 5-fold rotational symmetry. And so symmetry is an idea we can spend a lot more time on. And so we'll come back to that. But I just wanted to mention those 2 kinds of symmetry there. So aside from some weird problems, we've covered most of the stuff in 11.3 and 11.1. There's some things I haven't talked about at all in 11.4. And I want to do that since it's about angles. And then if there's any time today, we'll go to 11.2. Otherwise, that'll be our next topic. So some 11.4 stuff we need to contend with. And we've covered some of the stuff in 11.4, but there's a whole bunch we haven't. So 11.4 is mostly about classification of angles. There was a little of that in previous sections, like acute, right, obtuse, supplementary, complementary. Here's some other ones. So there's 2 situations that come up with the classifications we're going to do right now. If you have 2 intersecting lines, like say these 2 lines right here, we create 4 angles. Other situation is if you have a pair of parallel lines. Let's make a line parallel to that. So these 2 red lines are parallel. And then you take any other line let's change that color. You take any other line and use it to cut through those 2. That's another situation where the classifications I'm going to talk about come into play. Okay, so one type of relationship here, and you can kind of see some symmetry when we have 2 intersecting lines. So let's look at the blue case first. So in the blue case, this angle right here, let's call that angle A. And this angle right here, let's call that angle C. they're the same angle. And I'm going to justify that with a little bit of algebra. There's other ways to do it. Take this angle down here, let's say that's angle B, and take this angle up here, let's call that angle D. Those should appear to be equal to. Now, one thing that's going to be confusing for kids in a picture like this one here, is that these lines do not intersect at their midpoints. So we've got these shorter distances down here, and so some kids might argue that angle B is smaller than angle D because of the lengths of the lines surrounding them. And then what we can do is we can whip out measuring tools and, well, let's check that. See if it's the case. So I'm going to come back to this parallel group in a minute. Let's put that in my new slide. Oh, I broke something. There it goes. I did not mean to do that. Okay. So one thing I can note about the lines I have here is angle A and angle B are supplementary. Supplementary means they add up to 180 degrees. So if I take the measure of angle A and add that to the measure of angle B, oops, I get 100. Other things I can say. Are there any other pairs of angles that are obviously supplementary here? So A and B are supplementary. What else? B and what?
C and D.
C and D are. What else?
A is here to say, and B is here to say.
Yeah. What else is supplementary? C and D are. A and B are. How about A and D? Are they supplementary?
Yes.
Yeah. How about B and C?
Yes.
Yeah, so what we're going to find is as we move around two intersecting lines, adjacent angles are always going to be supplementary. Two angles are next to each other. So when I turn that off, it's powered off. Okay. So they're going to be supplementary. So I'm just going to make another connection here. Angle B and angle C are supplementary. They add up to 20. So I'm going to write that next. So if I take the measure of angle C plus the measure of angle B, they're also equal to 180 because they're next to each other. They're supplementary on two intersecting lines. Well, if both of these sums are equal to 180, they must be equal to each other. Agreed? And they both have something in common. They both have the measure of angle B in common. So if they have to be equal, what does that mean about angle A and angle C? They also have to be equal, yeah. So we just kind of reduce it down from there. Angle A and angle C have to be the same. And we can do the same argument with B and D. They have to be the same when we look at these supplementary angles in pairs. And as long as there's two straight lines intersecting, it doesn't matter where that intersection is, an angle is measured by the amount of rotation that happens. The length of the lines are irrelevant. And that's a common confusion. So we just whip out our protractor and we double check. And like GeoGebra would be a fun way to do that. Some kids might like playing with it. Now, problem, GeoGebra does have a lot of tools, so it can be overwhelming, but I'm always surprised at the things kids can figure out on a computer. It regularly blows me away. So let's see, let's bring up a new page. Where is new file maybe? New. Do I want to save this one? Sure. It is a equiangular pentagon. Almost too much work not to save. Save it. And come on, give me my new screen. There we go. All right, so let's get, see, I don't think I need a grid here. That would just complicate it. So I'm just going to draw a line and then draw some other line. Actually, maybe I should have done line segments. Now let's undo that. Ooh. All right, let's make line segments. So I can draw a situation like I have on the board there with two intersecting lines. And then we could ask kids, which angle is bigger? This angle up top here or this angle on the bottom? And can you see that somebody might try to argue that this angle on the top is bigger than the angle on the bottom? And so then we just say, okay, well, we can put our protractor down on a piece of paper and measure and see, and that's always a good thing to do. Or, let's see, I guess I need the intersection point to measure those angles. And I can say, let's ask GeoGebra what the angle from C to E to A is. And GeoGebra says, let's make it bigger so everybody in the audience can see. Options, font size, 24. Okay. Is that visible out there, Debbie and Kelly?
Yes.
Okay. So it says that angle right here, come, move please, there we go, is 29.86-ish degrees, and then I can try to do the same angle measure down here. And in GeoGebra you have to go clockwise with the central point in the middle of the click. And it says, yeah, that one's 29.86 too. So they're the same angle, regardless of that extra space can be deceiving up there. So we'll talk more about angle in a few minutes. And those kinds of angles are called vertical angles. Okay, vertical angles. So A and B are supplementary, but A and C are vertical. Let's look at that other situation I have here. And then otherwise, two lines intersecting, there's four angles, there's kind of not too much you can do besides supplementary or vertical. However, if you take three lines and intersect them, there's a lot more stuff going on. So let's take a look at this picture. All right, so these guys are here. So I'm going to label some angles, and let's see if we can make some connections about them. So let's say maybe I'll start up here. I'm going to call this right here angle A, and that is angle B, and this one C, D, E, F, G, and H. So, and keep in mind, this line right here is parallel to that line right there. The red line bunch of parallel. So let's see, what do we know about, for example, angle A and angle B?
Supplementary.
They are supplementary. And I used to, when I was young, have trouble remembering the difference between supplementary and complementary. And then someone told me, well, sup has the word like super in it, like Superman. Comp is in super. So supplementary, super, that's bigger, that's 180. Complementary means they add up to 1. So that always helped me remember that. So complementary angles add up to 90, supplementary angles add up to 180. 180 is bigger, it's super. Okay, how about angle A and angle G? What kind of angles are those? A and G. They are vertical angles, correct. And one thing about vertical angles is they're congruent or equal. Vertical angles are congruent. Do you see any other angles that might be equal to A and G? C and E, yeah. And so there's relationships between A, G, C, and E depending on how we decide to put them together. But they are all congruent. So just make a note of that. Angle A, angle G, angle C, and angle E are congruent. And then there's special names that go with them in pairs. So let's go over those. And one interesting thing about this class is there's a lot of terminology in geometry. And so I've been avoiding it because we've been having too much fun with the projects. It takes time to get into all the terminology. So sorry we put off so much terminology. That's mostly what we're doing today. All right, so we go to a new screen because I ran out of room. Okay, so here are my angles again. So let's see. Let's take angle A and compare it to angle E. Now, they appear to be congruent, right? And here's how I would describe them. They are on opposite sides of the black line, right? And that black line is either referred to as a transversal or a transect. So they're on alternate sides, so they're alternate. They're also kind of on the outside of the parallel lines, so they are called alternate exterior angles. Does that make sense? Alternate sides of the transversal, they're that black line, and they're exterior to the parallel line, so they're alternate exterior angles. If we take a look at the relationship between angle A and angle C, well, they're on the same side of the transversal. Let's see, A is like exterior of the parallel lines, but C is interior of the parallel lines, so that really doesn't help. But one thing I can say is they're kind of in the same position, aren't they? They're both in the upper right corner of one of the parallel lines in the transversal line. And so they're called corresponding because they're in the same position. So those are called corresponding, the same position. The positions correspond. If they're corresponding.
Are they going to be equal?
Yeah, so all the things I'm going over the descriptions of how we relate congruent angles in a system like this.
Okay.
And for some reason, people a long time ago decided this was important. Eh. It's kind of boring. Is it that important? Eh. There's a lot of interesting geometry based on these relationships. Some years I think it's important, some years I think it's not that important. But I'm going to mention it because it's in the book. All right, let's see. What else could I compare? I've compared A to E, alternate exterior. I've compared A to C. Those are corresponding. Another combination we might take a look at is, let's see, G and C are the same. What might we call those? Are they alternate? The black line, opposite sides.
Yes.
Yeah.
Are they alternate corresponding? No, they're
Well, they're not corresponding. They're not in the same position. They're flipped, right? Are they inside or outside the parallel lines? What was that, Debbie?
Alternate interior.
Yeah, they would be called alternate interior angles is the common phrase for that one. And that's another way to say you have congruent angles. So angle G and angle C are alternate interior angles. And I can't handle any more terminology today. So I got one more thing I wanted to mention. So we've covered most of the stuff in sections 1, 3, and 4. 1, 3, and 4. So now I'm going to back up to section 2 for a minute. Now, most of section 2 is about converting metric units, converting English to metric, and we'll do more of that later. At the end of section 2, they talk about some angle ideas, and I want to talk about that idea right now. Now, I'm calling this a new way to measure angles because it might be new to you guys, but it is not like new in the world. This has been around for a long time. And I'm going to go into GeoGebra to explain some of it because I can draw pictures better there. So just the old ways we had to measure angles. We could talk about part of a rotation, which I did in the first part of today's talk. And we could call it a rotation or a revolution or a turn. And the second popular way was the idea that there's 360 degrees in one rotation, or one full rotation. So half of a rotation would be 180, and a quarter of a rotation would be 90, and so on. Now, a rotation's a really good idea because it makes sense. I make a full turn, I'm facing the same way I started. 360 I mentioned earlier is kind of an arbitrary number. It's as arbitrary as saying there's 12 inches in a foot. Why is there 12 inches in a foot? Because someone decided that a long time ago. There's no good reason for it. Why is an inch as long as it is? Because someone felt like it. Same thing with 360. Why 360? There's no really good reason for it. So when I think about rotations, I think about, or angles, I think about rotations, I think about turns, I think about spinning. Spinning makes me think about circles. So I'm going to go into a story about circles here. So let's make a new file. And I don't want to save that one. And let's just go into geometry mode. All right, so let's see. I'm going to make a circle with a radius of 1. There's a circle with radius 1. And then I'm going to make another circle, starting with that same center. And this one, let's have radius, how about 4? Okay. And let's make another circle at the same point, and let's have that one be radius, how about 7? Okay. And let me recenter this a little bit. Excellent. And then I'm going to set a couple of rays out here. So let's put a ray out this way. How about right about there? Let's put it actually on there. And then let's put another ray right around here, say. All right, so we're going to do a little math with this, and you're going to have to think back about formulas you learned before, and we'll come to this again in chapter 14. By the way, I was thinking about covering chapter 14 next, and then if we have time, jumping back into 12 and 13. But we can talk about that after. So let's see. I've covered part of this circle here, and would you agree that in any one of these circles, the angle between these two lines is the same everywhere? Whatever that angle is. Doesn't matter whether I use these 3 points to measure, or if I use the points on this circle to measure, or if I use the points on this circle to measure. That angle is whatever it is for every one of those circles. So another way, and here's another thing. Are these circles the same shape?
Yes.
Yeah, oh, every circle is the same shape, right? Kind of a silly question. I mean, they're circles. They're all the same shape. They're all perfectly round. So all circles are similar. And so similar figures have a feature where if you take parts of them and divide them, you always get the same answer. Okay, so let's play with that idea. Every circle has a circumference. So let's get, ooh, I made a whole new file accidentally before. Huh. Let's get rid of that. Get back to this one. All right, anybody recall the formula for circumference of a circle?
Diameter times pi.
One more time.
Diameter times pi.
Excellent, diameter times pi. So circumference is often given c, and it's the diameter times pi, or pi times the diameter. Other things, 2 radiuses make a diameter. So some people remember the formula that circumference is 2 times pi times the radius. And so what I can do is I want to take the following ratio. I want to compare circumference on a circle to the radius. Okay, so let's see. If I take my little circle, its radius was 1, so its diameter was 2. So my little circle, it had a circumference of 2 pi. It had a radius of 1. On my medium-sized circle, I'm pretty sure I gave it a radius of 4. Let's see, where did that go? You can always double check with GeoGebra's line measuring tool. So if I measure from the center to the edge, GeoGebra says, yes, that is 4. And the other one, I'm pretty sure it was 7. Yeah, it was 7. Okay.
back here. So the middle one, let's see, radius is 4, so the diameter was 8. So we had an 8 pi circumference, and then I divide out the radius, which is 4, and my big circle. Let's see, radius was 7, diameter is 14, so it had a 14 pi circumference with a radius of 7. So I have 3 different fractions here based on those 3 circles. The first fraction, well, dividing by 1 is pretty lame, right? So it reduces down to 2 pi. When I clean that up. What's pi? Anybody remember approximately?
3.14.
3.14. So if I double that, that means its measure here is approximately 6.28. If I round it to 2 decimal places. Well, can I clean up 8 pi divided by 4? What's that clean up to be? 2 pi. And 14 pi divided by 7. It's 2 pi again. And that just goes to the fact that when you take ratios of like parts of figures, if the ratios are always the same, those figures are similar. They have the same shape. All circles have the same shape. So that's just a relationship between the idea of a proportion and similar figures. And so it turns out we can use that idea to measure angles. And here's the way it works. What we do is, to talk about what an angle means, we say, just measure the arc length that you get. And let's see, I think GeoGebra might have an arc length tool here somewhere. Circular arc. Will it measure it for me? Let's see. So if I go, what does it say to do? Hang on, I can't read that. Oops. Oh, not what I meant to have happen. Get back here. Minimize. All right, GeoGebra circular arc. Select 3 points on. Get back here. Circular arc. Select center in 2 points. Okay, so if I go here, here, and here, it gives me that thing right there. Will you show me a label for it? Maybe. I think I'm going to need the algebra window on this. Properties, name and value. Let's try that. So that could be right. Okay, let's try that again. So I think GeoGebra is telling me that if this radius here was 1 inch, then this arc there is 3.38 inches. Okay. So I'm going to see if I can get it to measure the other arcs here. So let's go from here, there, there, and I get this new arc. Okay, properties, show me the name and value. And this should be a slightly smaller number, 1.93. We're going to sneak inside on this one here. I think I better blow up the font. Options, and we're almost done with this part. Bear with me. Font size 24. Okay. And then finally, I'm going to do this little itty bitty one inside here. Boom, boom, boom. And, uh-oh, nope, that's not what I wanted. I just want the arc, please. Uh-oh. Oh, stop it. Escape. Pointer. Is that the arc right there? Nope. Nope. Maybe I gotta zoom in to get it. Okay, please give me arc. There we go. Sometimes it's hard to get to GeoGebra to point to the things you want, which the algebra view makes it nice. Okay, so that one's 0.48. Okay, so here's what I want you to do next. Write down each of those numbers. So let's see. So what I want to do is what is the proportion of the arc to the radius for each of these? So for example, for the big one, that would be 3.38 divided by 7. For the medium one, that would be about 1.93 divided by 4. And for the little one, it's 0.48 divided by 1. I'm going to steal those numbers into my sheets and see if that yields any good results. Are two circles similar? Yes. That means their corresponding pieces should be proportional. Screen clipping. We're going to steal these numbers here. All right, so what we need to do is compare calculator-wise. We are comparing the ratio of the arc to the radius. So for the big guy, it's about, and again, it's approximately 3.38 over 7. For the medium-sized guy, it's about 1.93 over 4. And for the little guy, it's about 0.48 over 1. So I need you to whip out a calculator and reduce each of these fractions, and let's see if anything significant happens. If these arcs or these circles are really the same shape, then I think these ratios should all be the same number. So 3.38 divided by 7, Google says is about 0.48. I've got some rounding error because pi is involved. What was the other number? 1.93? Divide by 4, and I get about 1.93, 0.48. So each of these arc lengths divided by the radius of the circle it lives in leads to the same number all the time. So this gives me another way to talk about angles by talking about the length of an arc compared to the radius to make that arc. So back to my notes here, and there's two ways to think about it. So people realized this a long time ago, and they thought, whoa, wait a minute. You guys were using 360 degrees. Where'd you get 360 again from? Oh, it's close to the number of days in a year. Well, that's silly. We need close. Right? These other people said, pi is a very special number. And we've known that for a long time. It's way more special than 360. And they found a way to relate angles to pi. And this measurement is called a radian measure. Now, this is something you're very unlikely to teach in elementary school. But I think as adults and teachers, you ought to be aware of this idea. So the idea of a radian measure of an angle. And so one way to think about it is you just take the arc length and divide by the radius. The resulting number is what's called the radian measure. So that's how you calculate radians. But it turns out they're slightly easier to work with than that, and so I'm going to go over that next. So the important, if that seems kind of complicated, here's one way out of it. All circles have the same shape. And I could extend that to be a little more specific. I could say all circles have the same shape as a circle of radius 1. So I can use a circle of radius 1 as my guide. So let's do that. And so, by the way, if a circle has radius 1, would you agree that dividing by 1 is pretty boring? Nothing happens. So on a circle of radius 1, the arc length is all that matters to describe the angle. So let's check this out, and then I'm almost ready to shut up. Circle. So let's see, if I try to make a circle with this tool, it's kind of hard. How do I force an ellipse into a circle? Anybody remember? Yeah, hold down Shift while you're making it, and that'll force it. So I'm holding down Shift now. That'll force it to be circular. And then I'm going to split this circle up a little bit with some lines. So let's try to cut it right down the middle vertically. That's pretty close. And cut it horizontally. About right there. And then on the circle, I'm just going to make believe that the distance across here, so from the center to the edge, my radius is equal to 1. What's the circumference of this circle? Let's see, that would be 2 times pi times the radius, which would be 2 times pi times 1. The circumference of this circle is called 2 pi. Since the radius is 1, this is referred to as a unit circle. Unit meaning 1 for the radius. So check this out. If I were to start at this point right here, and I were to travel around this circle and get back to where I started, how many degrees is that angle?
360.
That's 360 degrees, right? Pretty straightforward. So just a note, 1 revolution is equal to 360 degrees. I could also say, didn't I actually cover the circumference as I did that? And on a unit circle, the arc length is radian measured. So I can say 360 degrees is the same thing as 2 pi radians. Sometimes you'll see it abbreviated RADE. I'm going to write up the word radians. So radian is just an alternate angle measure. It has more foundation in geometry than 360. 360 is arbitrary. Now, how many people, is this the first time you've heard of radians? Greg, first time? Debbie?
Yes, it is.
Okay, so this is going to sound weird and foreign. It's like trying to work in base 7. It's like, what the heck? So it takes some getting used to. But the bottom line is 360 is an arbitrary number somebody picked for their own cute reasons. Pi is not arbitrary at all. It's this universal constant. And so what I have now is a way to talk about angles that has a valid justification in the geometry of a circle and an angle. And when you agree that circles and angles kind of fit well together, and so getting used to radians is like getting used to the metric system. You just start using it and then you get used to it. Will you guys ever have to get used to radians? Unfortunately not, I'm sorry to say. But I can mess around with them in a relatively easy way. Like if I start here, oops, do that. If I start here and I go to there, I've gone a quarter of a revolution, right? How many degrees have I gone? 90 degrees. And, oops, not percent. There we go. And I've gone a quarter of the way around my circumference. Okay, so let's see. 2 pi over 4. The 2 goes into the 4, so that would give me pi over 2. So that is what we would call the radian measure for this angle. And it's just something you get used to. Like, didn't once upon a time you have to get used to that 90 degrees made a right angle? Or that a right angle means it's 90 degrees? Why 90? Well, why 90? Well, because it's like a quarter of a rotation and 360 degrees is a rotation. So again, the 360, this is an arbitrary thing people made up a while ago. It's a nice number. I like it. I'm used to it. But there's nothing special about it. Radians, there's actually something special about it because of pi. Revolution, yeah, I can go once around the circle. That's pretty meaningful. 1 revolution. All right, so we're out of time for fun with math today. So I think at this point, I was reviewing the book earlier, I've covered 94.5% of what's in sections 1, 3, and 4. There's a couple things I skipped, like dihedral angles. They're cool. We can talk about them in chapter 14 in a better context. I've covered 1/4 of section 2. I haven't covered the metric system. I'd like to combine the metric system with chapter 14 where we do other measuring stuff. So keep in mind, chapter 11 is an overview of lots of geometry, but we're skipping out on some really cool things. So what I'd like to focus on next, we still need to finish up 11.2. We need to go over the metric system. That's important. And then we're going to take the idea of the metric system and combine it with measurement stuff. So let me show you the book quick to give you my plan for the rest of the term. And you can say something like, hey, I was looking at the book and I really want to do this instead. Feel free to overrule me. We have a small class and the syllabus says we have to cover geometry, which is a very diverse field. So we have a little freedom here. It's a pretty big field, yeah. So let me bring up the table of contents of the book here. So I'll tell you what I was thinking, and then you guys can think about it over the next couple of days, and on Wednesday we can decide on how we're going to attack the rest of the quarter. Come on, you can do it. Greg had mentioned he had a problem with one of the homework problems. We can troubleshoot homework problems next class. I haven't made any time for that. Okay, so chapter 11 is the intro to geometry, and can't I make the book show me that? Let's see how I go back. Contents, there we go. Okay, chapter. Okay, here we go. So chapter 11 was the introduction to geometry. We're covering a ton of stuff. We hinted at symmetry a little bit, and there's a whole bunch of symmetry in chapter 12, congruence and similarity with constructions. There's some really cool artsy stuff we can look at in chapter 12. Next page. Chapter 13, more congruence and similarity, but with transformation. So sliding things around, stretching things. There's some fun stuff there too we can look at. I want to cover a little bit of stuff in 12 and 13. We can't cover everything in the next 3 chapters. I was thinking about doing some stuff in chapter 14. So some things I think are important in 14. 3-dimensional shapes and areas are an important thing. Areas of polygons and circles. We've talked a little bit about that, but not a lot. More investigation of the Pythagorean theorem could be a cool thing, but maybe you feel in your algebra classes you beat the Pythagorean theorem to death. Surface area is kind of cool. I don't think I'm going to get into volume, mass, and temperature. That's some cool physics stuff. So unless you guys have an interest in physics, we could skip over section 5. So I was thinking it'd be fun to play with areas in the Pythagorean theorem and some 3D stuff. And then we could come back after that, we'll have some more time, and hit some of either transformations or constructions. So I would recommend over the next couple of days to finishing up homework, work on the activities, and take a peek of what's inside chapters 12, 13, and 14. And if you have a strong opinion, like I do want to cover this, I don't want to cover that, let me know, and we'll try to make a decision about what to try and finish off the term with, because we are halfway through now. So if you can, give me some feedback on that. Otherwise, I get to pick, which I always have fun with this. So I'm not too worried about that. But if you have a strong opinion, like, ooh, I don't know much about that, I'd like to learn more about it, then let me know. Sound good?
Yes.
Okay. All right, so let's see, that's it for today. I'm going to be plugging your grades into the grade book the next couple of days, so that should be up to date by Wednesday.
Have you graded the tests?
I am still thinking about how to grade the test, but I've read everybody's test.
Okay.
So I will have grades on that by tomorrow.
That sounds.
All right. What's that?
That sounds scary.
Oh, it's just everyone put out a slightly different attack on it, and everybody had good stuff. It's just hard to then decide how many points that ought to be worth, because it was an analysis question.
Mm-hmm.
Questions like that are always hard to grade. So I want to try and come up with a method that's equitable.
Okay.
So I'm almost there. So don't worry about it. There was a lot of good stuff. Let's see, there was one other thing. Oh, yes, I remember now. We talked about, and Greg followed me around with the camera to kind of finish off the ideas in Activity 7. So I traced out on the ground the idea of coming up with exterior angles. And so what I'd encourage you to do for Activity 8 is to get a piece of tape and make these figures on the ground somewhere, or chalk maybe, and think about walking around the figures to kind of get an estimate of measuring angles. Because we're doing a little work with interior angles of these star type figures, and we'll play with that more in the next class.
Okay.
And so I brought a roll of tape this time, so that's one thing I was going to do today if we had time, is make some stars with tape on the ground and try and answer some of the questions in Activity 8 based on that. So on Wednesday the plan would be to answer any homework questions, go over the metric system, and then finish up any activity questions people have, in particular the star lab here, which we haven't talked about together yet. Okay, that's it for fun today. I will see you all on Wednesday. And Debbie, hopefully the recording worked this time. The last one I came out sounding like an alien.
Yeah, from when I logged on, you sounded normal this time, so it probably did.
It probably worked okay then. Good. All right. Thanks.
On the 11th, so not this Wednesday, next Wednesday, I have my Quest academic planning meeting with Miriam Monk.
Okay.
So I won't be logged on to the actual live class. I'll just have to watch it after my meeting.
Okay. Is your meeting in Hermiston or here?
No, it's in Pendleton, because it's like everybody that's. Yeah, well, it's scheduled for 4:30, so I'll get off work at 3:30 and then drive to Pendleton.
Oh, right. Okay. All right. Well, I'm usually here till a little after 5, so if you have time to stop by and say hello after, please do.
Okay, sounds good.
All right. Okay, I'll see you later.
All right, thank you.
Yeah, bye-bye.
Bye.